people are just unable to find materials, and that's just the usual issue of organizing lots and lots of information across multiple channels. Vlad has joined. That's great. I know Vlad was feeling a little under the weather, so it's very kind of him.
Yeah, I'm not feeling too great, so I'll probably be a little sparse, but you know, I figured out at least listen in.
Sweet. Well, Alex, I think in terms of agenda, I would love to give you sort of front and center right at the top of the hour. Talk about your delegation model, the DCC consensus model, and get some feedback and let people, poke and prod the ideas. And then if there's any time after that discussion, I will happily go over some exciting work that Mike Stay and I have been doing, where we have a new approach to deadlock freedom, which generalizes to express the kind of liveness characterizations that Vlad has been playing with. So I can walk people through those formulae and how they're interpreted in the model checker, and then I can also walk people through the storage proposals for the by proposition version of Casper. Those are also the sort of summaries of those are in the mobile process calculator for programming the blockchain. So people can just read about those offline. Let's see. Did Vitalik join? Not yet. All right. Well, let's give one more minute, Alex, and then we'll let you dive right in. Did everyone who are celebrating the holidays have a chance to celebrate?
Hey, B.
Hello.
Hey, Vitalik.
Hi, Greg. How are you?
Good. Well,
enjoying your Christmas?
Indeed, yes. And you?
Yep.
Oh, good.
Hi, Vitalik. Nice to meet you finally. This is Alex.
Hello.
Very fun.
So I guess we have a quorum. So why don't we go ahead and get started, Alex? I'll just hand the mic over to you and let you and drive us through a description of DCC, and we can chat about how that relates to Casper. I think Rick and I are sort of converging on a similar view.
So first of all, I feel really self-conscious because you guys been kind of discussing these things for a really long time, and I kind of been watching from the sidelines a lot. And even though I read a bunch of papers, I think I barely know what the current state of Casper thinking is, Greg. So I know that because of that, I feel rather prepared to
Yeah, don't worry about it. First of all, let me say I totally understand what it feels like to be self-conscious, but but here the aim is really to expose the ideas and have fun discussing them. Like I tend to think about it more like music, right? So if you're jamming. And if you play the wrong note, play it strong and wrong, baby. It doesn't matter. Let's see.
Will do. Okay. So basically, I know that you and Rick have looked at my paper a little bit, have some idea of what I'm thinking.
Yeah.
And I think I haven't really ever thought of presenting this to somebody who hasn't, but I'll try.
Okay.
So the things that I notice when I look at other proof of stake systems is that I notice that a lot of the algorithmic complexity comes from the way that you structure the kind of the way that signers alternate to sign blocks. And I noticed that, to me, that problem comes from this kind of idea inherited from Bitcoin, really, in many cases. And again, I don't know how Casper works right now, so I can't say. But in many other proposals that I have seen, it seems like people are kind of committed to this idea that the block signer is, in fact, the party that receives the transaction fees. And so then there comes this complex question of how do you structure this fairly, but also in a way that the blockchain doesn't stop if somebody goes offline. And so the one sort of component of what I'm proposing in DCC is this idea that you kind of eliminate that complexity by structuring the distribution of transaction fees and issuance, where it doesn't really matter who signs the block, as long as, and all signers do receive a portion of the transaction fees, provided that they're currently have an active status. Right, and I'll talk about what that means in a bit, but I think, doing it that way creates a situation where basically any signer will very happily accept a branch signed by somebody else, because they will still get their portion of transaction fees. Everybody is incentivized to ensure liveness of the network.
Yeah, just a little spoiler. Yeah, I think we mostly already do this with Casper. But we do have to give a small extra incentive to the person who gets the block. Otherwise, there is no incentive to actually include transactions.
Right. So I think the challenge here basically is who actually, first of all, who controls whether or not a transaction gets included, right? So like, what is the process that decides if I send a transaction, is it going to get into the next block? Is it going to get into the block after that, and so forth? Then, depending on what that process is, you pretty much always want to kind of perfectly pair up the incentivization with the control, right? So if, let's say, the next validator number 53 is the one that's has the ability to unilaterally include it into a block, then validator 53 should be the one that gets 100% and exactly 100% of the transaction fees.
Yeah. So
Can somebody explain this to me? I don't think I understand this yet.
So
Sure.
the challenge. So the challenge here basically is that if you have a protocol where transaction fees are split up between multiple validators according to some prescribed formula, then the problem is that it is extremely difficult to avoid accidentally creating incentives to basically pay transaction fees out of band, right? So,
right, but there's still this idea that you have a transaction fee policy, and extra band would go to the person who included it. But anything else,
it's an important caveat.
Yeah, because my version of Casper only uses transaction fees. That's how I pay for finality, for example.
Right.
Whereas pay for finality with issuance.
Mm-hmm.
So that's why I think that caveat is necessary for this conversation. Really, basically, there's mandatory fees which can be redistributed and optional fees which cannot.
Mm-hmm. Yeah. So next question, I guess, is that it's quote remove the complexity of having an algorithm that assigns one validator to each round. So I'd be interested in hearing what is the actual process that creates blocks.
So okay, I feel a little stupid because Vitalik, what does it mean to pay transaction fees out of band?
So let's say, for example, that I make a private agreement with some validator, and I agree that if they prioritize my transactions and always do the best to get them included as quickly as possible, then for every unit of gas that gets successfully included through them, I will pay them, let's say, 0.0001 cents in Dogecoin.
Oh, I see what that means. Okay, so that means that somebody can basically pay somebody to create an unfair situation.
Well, it means there's a market on scheduling. And
there's a market on scheduling.
And there's no way to avoid a market on scheduling. It's actually impossible.
Well,
but you can have a mandatory minimum fee.
Yes.
Right. Okay, I see. I see. Okay, that makes sense. I think the way I was thinking about this. So then the second piece that kind of went into my thinking is that basically the way that I work with delegation is one where so just to start from the beginning, because not everybody has seen my paper. So my understanding of delegated proof of stake is that more people will lock away collateral than the people who actually. First, to increase the cost of attack on the network, we want everybody to be able to delegate, and that delegation is like this really important piece where the entire community puts its weight between the towards the block signing in either direct or indirect way. The direct way meaning you actually sign the block. The indirect way is you somehow delegate your funds. I call them signing power. It's not really, of course, transmitting any crypto asset at all, but it's kind of delegating the power that the crypto asset holds through some mechanism to the person who signs the transactions. And my thinking was that if you do that from the very low level and at the lowest level, that you don't have people lock it away, and that you can actually delegate active liquid funds to active participants in the network, some kind of transaction signers or observers, then you will ultimately kind of stand the chance of increasing the cost of attack tremendously by.
Can I ask a question?
Yeah.
If I delegate my coins to someone who is Byzantine, do I lose my coins if they end up losing their coins for being Byzantine?
No, you don't.
Okay, so basically, this is like kind of not a security deposit. It is just like
it's a vote of confidence of some kind.
Okay, and how does it? Do you know how it contributes to the score of the fork?
Okay, so here's how. So the way this works is let's imagine for simplicity purposes that there's only two levels. One is basically like individual users and clients and wallet holders, and one is the number of people who are active in signing transactions. Then the way the delegation works is once you delegate your signing power, there is a decay that is applied automatically and is time dependent on what percentage of your power is in fact active for transaction signing. So let's say that somebody who holds 1,000 coins delegates 1,000 coins at point T, then at point T plus X, the delegate will only have half of that power to use. And at point T plus 2X, it will have a quarter. It kind of decays exponentially. Mm-hmm. And then the way it contributes to distinguishing the correct branch, the most active branch from inactive branches is by calculating the total delegated amount of signing power that went into the particular block that includes the decay.
Okay. So only the delegated signing power and / direct signing power counts here. There's no so in your model you have no notion of security deposits and economic value.
Yeah, yes, that's correct. The security deposits are still done, but they're basically auctioned off, where somebody who puts the biggest security deposit will become the candidate, or like N people who put up the biggest security deposit at an auction will lock them away and become active, and then people can start delegating things to them. But the amount of the security deposit only counts at level 0 at the same level as everybody else's holdings. And the way that the security deposit increases over time is because as this becomes more profitable for signers, people will be incentivized to put up more security.
So, but wait a second. The money that's going to the signers, in the sense of the people who are delegating, doesn't go to the security deposit holders. Is that not correct?
So the way, okay, not sure I understand your question. So let me just quickly recap. The way that somebody becomes eligible to receive delegations is by participating in a collateral auction. So the collateral auction runs at certain intervals, and basically it selects according to some parameter n the most collateralized players on the network, and those players are the only ones that are eligible to receive delegations.
So this is akin to the bonding period in Casper.
Well, so that makes sense. But the thing that I'm not understanding is, so here's like my feeling, right? By diverting some of the transaction fees and revenues to the delegators, we're going to have less security deposits, which means that we have less economic security from the point of view of like a bribing attack model, or like an oligopolistic model. The sense in which we have more security is that there's physically a larger proportion of the overall supply of coins that are involved.
So let me answer that, Vlad. So the second piece to this, which I haven't mentioned yet, is the idea that I want the delegators to be actively participating in deciding who the right delegates are. So I set up a structure where you have a censorship-proof way to redelegate your funds to different members of the network if you don't like what the current members are doing. And that is
that makes sense. But if there's no value at loss, then you could just pay for these votes.
Let me think about that.
Yeah, but in general, let me say that I really like delegation, and I think that delegation is something that we should add to Casper in like a later iteration. However, I feel very strongly that if you put your money with a delegate and that delegate is Byzantine, that you should lose your money.
Yeah, yeah, I think that makes the most sense.
And don't we already implicitly have delegation in Casper?
Yeah, we do, because of signature abstraction.
Yeah.
Yeah, but I mean, like we haven't thought too much about like building that infrastructure out. But yeah, so we can totally build it in with the soft fork. Basically, it's not even a soft fork.
I actually disagree, Vlad. Now that I think about this, because I think the assumption that I'm using here is that basically by opening up the delegation to every economic player in the network, not just a small set of them, the state that you create is that most people are in fact interested in the network actually working. And so your percentage, the relative percentage of funds owned by Byzantine players, both clients and delegates, is assumed to be pretty low.
Yeah, that's a weird assumption to me. I don't quite. It doesn't really fit in with the Casper, oligarch, resistance to cartels sort of thing.
What are Casper persistent cartels?
I mean, I'm sorry, maybe my mic's not good. I mean, the whole idea is that really you should be able to still have a functioning network even if there's a majority of the value at stake that is Byzantine.
Well, but I'm not talking about value at stake. I'm talking about economic value of the network.
Yeah, so I mean, I think that makes sense. And
that's at stake, actually.
Yeah. So and this is kind of what I was saying earlier, where the reason why it increases security is basically because there's a bigger proportion of the coins who are participating.
Yes.
Not because of increased economic security. Because like if everyone was rational, you could pay them, and actually it would cost less in this model because they don't lose their money in the case that these actors are Byzantine.
I mean, you can potentially envision a situation where you get fined in some circumstances when your delegate misbehaves.
Yeah, to me that makes tons of sense.
Yeah, I think that's pretty much a requirement, right? I mean, I commented in your fines section that like you absolutely need to have a fine for that behavior, or else you're actually incentivizing a collusion between validators and clients, because even though the validator gets fined for bad behavior, the clients don't, and the clients are endorsing the validators. So if I want to be a bad validator, what I do is I pretend to be clients.
Yeah, exactly.
What you do is what?
I pretend to be clients.
Well,
But the idea here, Rick, is that like, if 80% of the ether is participating in this, it would be hard to pretend to be a lot of them. Another way to say it is like, I would just go bribe some people, be like, hey, look, delegate me, I'll pay you a slightly higher return than normal.
Yep.
And they don't get penalized for your bad behavior, and then you get all this extra weight.
But that's what I thought Rick meant when he said pretend to be clients.
Yeah. Bribing, or same difference.
Yeah.
okay, well, I guess I need to think about this. I certainly I completely understand that the proposal I'm making is not actually for Casper, because I don't think any of this would fly with like the Ethereum way of thinking. I was more gearing this because basically the assumptions that I'm making, they come from a kind of a thinking where I want people to actually have both social and digital consensus about things. Like I think if you try to exclude social factors from blockchain, from the blockchain algorithms, then you end up in a situation where it's very, very hard to create the right economic motivations.
No, I think that insight is actually quite important.
I think we all agree with that. The question is really just like, where is that done, right? I mean, is it done through risk-free signing at the protocol level, or is it done somehow extra protocol, or which is kind of my feeling is that for example, for finality, there's in-protocol finality, which is like when your client decides it won't revert, and like extra protocol finality when there's like broad-based consensus on some recent state root in the community, and like the social finality is the one that's really important, because in the event of like any kind of contention, that's what's going to decide where reversions are going to occur.
Yeah, so I think we all agree on that core insight, and then sort of my sort of take on it is that's why I work on federated systems, right? Because in a federated system, the social and economic incentives are automatically in alignment. So I think that's sort of the extreme version. And Alex, you're trying to do something that's a little bit in the middle, and then Vlad's way on the other side. So I think it's definitely a good idea that we pretty much all agree with. It's just a question of the details.
Yeah. I definitely like this idea of the decay. That's quite nice. And that gives an interesting way of thinking about the bonding, for example, and also delegation is naturally nested, right? So that
that was the last piece. Is that basically in order, like in a two layer structure, you kind of require everybody to like watch things in order to like fix things if they go wrong. But then basically in order to ease up the connectivity requirements on individual clients, you basically introduce a middle layer wherein you have different decays at the different layers, and then the very bottom layer can basically decays very slowly and watches the network the least amount of time, and only comes in a situation where everybody is Byzantine and you have to fix that. Or and at the middle layer you have somebody who kind of can go down for extended period of times and decays much faster, but is still mostly present. And at the top level you have people who are absolutely present at all times, and they will they will lose their signing privileges if they go offline, and they decay very, very quickly. And that also eases the throughput. Basically the delegation transactions that suddenly become required due to decay are structured in such a way that there doesn't have to be a lot of them to have in the network for the network to operate.
Yeah, I mean, the compositional delegation sounds kind of interesting. Anyway,
I think that basically covers most of it. And at the end of the paper, I make a few notes about that same approach being used for governance at the level where, for example, you can have the entire market cap of the network decide on changing parameters in the network and changing the number of validators and changing the decay periods and stuff like that. But that's kind of like a footnote. I haven't really thought much about security issues related to that. But in my way of thinking, I think that's like really important, because again, participation in the decision making on the network of the economic holders, to me, is critical. And also being able to change a lot of the different things in the network without forking is really critical.
Yeah, the issue that we normally come up against when we think about these things is that, like, there are lots of stakeholders who aren't coin holders and who aren't miners and who also need to be represented.
Correct.
Another challenge. What was that, sir?
Can you name them just for
my favorites? Clients, right? Clients, people who pay transaction fees but never hold much coins. It's people who use applications but don't hold coins.
Yeah, correct.
Yeah, and then there's also developers, and people who build services around the ecosystem, but who may not, actually pay fees or hold coins or mine. They might be making ad revenue, for example. So that's one comment I have. And another comment about your general approach, and something that I would like to see you think about is the kind of the cost efficiency of the security that you're providing. That's one thing that I try to stress sometimes, is like, I want to have really, really cheap, really low cost of consensus, much more than I care about having it never ever fail, because I believe that we understand failure modes and how to recover from them. And it sounds like your system has, it's really trying to prevent failure at all costs.
I don't think I agree, but what is cost of consensus?
The amount of fees and issuance that you have to do.
I think it's pretty low because you don't do expensive computations mostly. I don't understand why you're saying it's high.
Because more people need to be compensated, and so it seems like maybe there needs to be more compensation. So the way that I think about it normally in terms of deposits is that the amount of deposits that I'm going to get are proportional to the amount of interest that I pay. And I don't know how that translates into this world where you kind of sign but don't put any value at loss. But I imagine that it's similar going to be like, if you want 80%, you're going to have to pay, say, 4 times more than if you want 20%.
I think it's a question, Vlad, I think it's a question of organic growth, because when the network is small and cheap, you can have like 5 validators and you'll be fine. And when the network is huge and has like $1 billion in market cap, you'll have 1,000 validators and you'll have the transaction fees to pay them.
Yeah, but minimizing the cost is always a priority. No matter how big.
Clearly, I agree. Definitely.
Okay, cool. Well, so should we go on to some of the other things that we wanted to cover in the stand-up?
Yeah, I'd love to. First of all, but I really want to thank Alex for taking the time to discuss the model, and thank everyone else for.
Well, thank you guys. I'm really honored
to be
invited to this group. Thank you.
It's just a motley crew of people who think about this stuff. We're all just nerds here, right? So thank you very much. If unless people have other things they want to go next, I can quickly share the liveness discussion.
Oh, sure. Let me quickly give my new updated definition of liveness.
Oh, okay, yeah, go for it. Yeah.
Because it's like a little simpler than the one I gave previously.
Mhm.
Basically, the definition kind of goes like this: a view has liveness in a particular fault context 1 with respect to another fault context 2, if in all possible futures we eventually have safety in fault context 2, where there's a recursive definition of eventually, where in a view something happens eventually if it either happens in all views that are one step removed, which is to say that are future view only by adding one bet, or if it happens eventually in all futures of one bet removed. So I think it's probably equivalent to my previous definition where I had this like there exists an n in there, but it's quite a lot nicer because instead of having this there exists an n such that for all futures that are further than n apart we have the safety. It's just that in all futures we eventually have safety.
Coolio. Well, that's actually it was precisely your uttering that definition earlier when we were in Kenya, Nairobi. That made me think about the work that Mike and I are doing in terms of deadlock freedom, and relating that to your liveness definition. And part of that has to do with the fact that we have a very crisp formalization of eventually that's related to the ladle algorithm, and also related to the notion of eventually that one finds in Hennessy-Milner logics and other modal logics. Cool. Yeah. So I'll do a quick screen share, and people can see where these definitions come from. So part of this work is related to, Mike and I are about to submit a paper to LICS. This is Logic and Computer Science. And the focus of this paper, unlike the previous paper, is just on the modal portion of the logics that we generate. So just a quick reminder, we have an algorithm where you give us, the input is a specification of a computational calculus, like the lambda calculus or the pi calculus or the ambient calculus, or take your pick. Virtual machines also count, right? So if you gave us a spec in a particular input format of the Ethereum virtual machine, and you also tell us how you want us to collect the results. So collect them as lists or sets or trees or graphs. Then we will auto-generate a logic. So that's the context in which this is being discussed. And here we're focusing on just the modal connectives of the logic and how they are related to important aspects of behavior. So I don't know if this is big enough, but the very top formula is an extremely brain dead way of talking about responsive. So little RSP with respect to a namespace, quote phi. So namespaces can be thought of for Ethereum people, they can be thought of as essentially programmatically described groups of addresses. For the general picture, you might think of namespaces as like programmatically described groups of URIs. So in that sense, a namespace is roughly akin to what you could describe with a spec like XPath in the W3C standard space. Okay, so a process or a strategy or a program or something like that is going to be responsive if you can find an address in the namespace such that the program does I/O at that address and then goes back to being responsive. So that says that you can always ping it. In other words, it's always willing to accept an incoming message, for example. but that doesn't mean there aren't any internal components that are completely deadlocked, right? So if you put a queue, like a RabbitMQ queue in front of a program, then it's always willing to receive new messages up to the size of the queue, whatever that might be. And if you have a lot of disk space, that's practically infinite. But that doesn't mean that the program is actually making any progress. So what you'd like to do is to refine that with the notion of no deadlocks anywhere. And there are a couple of different ways there's several different ways you can go about that. You can look at the session types from Phil Wadler and others to look at one approach to no deadlocks, and that traces all the way back to ways of using linear logic to prevent deadlock. And there are other notions like stuck freedom. That was from Jakob Rehhoff and his colleagues. I worked with them in Microsoft while they were working on that. And then there's a cycle-free approach, which I utilized in the Highwire project at Microsoft. But this one is different, and this one follows kind of the shape of the execution formula in linear logic without being like the session type. So I can unpack that here. So it's the next formula here. So this is big responsive with respect to a namespace. And what it says is either you can input at a name in the namespace and then go back to being responsive, or there's some portion that's doing output only, and you don't really care what it's doing the output on, and in parallel with some portion that is responsive. Or it does some internal communication, and then after the internal communication, eventually, and that's this operator here, goes on to being responsive. Or it's a parallel composition of responsive components. So this is effectively, and this is what made me think about Vlad's idea. What this does is it distributes responsiveness all the way out to the components and stops at places where there's potentially internal communication and lets that churn for a while. Now notice that we're not guaranteeing liveness. So we guarantee no deadlocks, but we don't guarantee liveness because that internal communication might have some infinite prefix beforehand. So you'd have to put some kind of bound on that internal prefix, and that's precisely where you want resource consumption, like gas or some other mechanism to address that, and you can identify it specifically in the clause.
The way that's done in my model is that is in the fault context. The fault context will restrict which possible features we're considering, and that will in a fully asynchronous network, you will be able to have an infinite number of communications between two parties before anything else happens.
Yep.
But in an asynchronous network, that's like explicitly not allowed.
Yes, exactly. And so, and that leads. Thank you. That leads me exactly to this next formulation, which is a parameterization of the responsive predicate. With respect to an additional predicate C. And what you do is now you're sprinkling C down to all the components, right? So it's basically just responsive and whatever predicate you want to insist is true at the component. And so that predicate can be utilized to express fault context constraints, can also be used to express safety constraints. It can be used to express lots of other things as well. But this gives us now a generic characterization of precisely those formulas. So if I take C to be safe, then we're insisting that it's responsive and every component is safe, for example, which then corresponds exactly to Vlad's notion of liveness. So now we have a formula which is...
So I don't actually see where the eventually comes into all this.
Right. So the eventually has to do with allowing for there to be. Let me take a step back. The important point is that because we have both modal and spatial connectives, I get to decompose my formula into the shapes of the strategies. So remember, Vlad, we were talking about how adding intentional information allows us to tame complexity. So here, the formulae are expressed under the assumption that we have available to us specific strategies that we are allowed to check against the formulae. So then the formulae decompose in terms of the shape of the strategies. So either we can see for a fact that the strategy has a shape that is a parallel composition, for example. It decomposes into two components that are responsive.
I
Or,
have to head off now, so.
sweet.
Okay.
Okay.
Thanks for stopping by.
Thank you.
Later, Vital.
Later, and keep enjoying your Christmas.
You too.
Later.
Same with me. I'm going to sign off. Thank you, everybody, and hopefully we can talk again about these really fascinating things.
Absolutely. Thanks for coming. Thanks for joining.
Yeah.
All right, take care.
Bye.
Okay.
So then just to briefly answer your question, so the only place where eventually plays in is when we have the potential for internal communication, because what you want to do is you want to allow that internal communication and then eventually get to a place where you are responsive. So that's the
That's interesting. So the way that I kind of relate some of the things you just said to my fault context construction is basically that the fault context, I mean, is at least in the case of liveness, going to be given in behavioral types. In safety, I only need to give it in terms of the types of the messages that are produced, because like safety is asynchronous in my current, in all of my safety discussions so far. But so the fault context for the liveness discussion, though, is going to involve these behavioral types that basically say they will make certain communication.
Yes, exactly, and that's where the C would come in. Now, it turns out that all signature-like kinds of constraints can also be embedded in the behavioral types. So the safety is easily embeddable in the behavioral types. You're just not utilizing. Yeah, exactly. You're just not utilizing all of the other apparatus. You're just using a fragment of the apparatus.
Right. Yeah. Cool. I agree. Yeah. So you mentioned that there are some definitions of eventually from some other stuff. Do you want to cover those if you can?
Sure. Yeah. I mean, this all goes back to. So I'm sure you're familiar with the idea of necessity and possibility from sort of the usual old school modal logics, right? So like S4 and things like that. So there's a
Sure, Greg.
Okay, well, sorry. So in terms of the history of logic, you have this sort of ordinary propositional logic, and then eventually someone comes along and says, well, we can think about possible worlds in which different formulae get different truth assignments, or different ground level predicates get truth assignments, right? And then you want to be able to navigate amongst the possible worlds, semantics. And this was Saul Kripke, who said, well, eventually possibly and possibility and necessity are related to how you can navigate from one possible world where a truth holds to another, right?
Cool. That sounds neat.
Yeah. So that was I don't know, the 60s and 70s when that work was being done. And then around that time, Milner said, hey, I can take this possible worlds idea and I can relate it to the semantics of process calculi. And so Milner and Hennessy gave a reformulation of modal logics, where the possible worlds relation is mapped directly onto the execution tree of the process. Right. So when a process can do an I/O, then it can possibly take an action alpha, which is the I/O action, the input action or the output action. And then you use De Morgan's rules to get necessity out of that, right? So not possibly not is how you get necessity from possibility. And then eventually is just iterated possibility, right? So from here it's possible, from here it's possible, from here it's possible.
Oh, cool. Yeah. Okay, great. That's very similar to my definition of eventually.
Yeah, exactly, right. Good. So we're beginning to make contact with the rest of computer science. That's awesome. Yeah, so that kind of gives.
I don't know. You can make contact without being.
Yeah, no, I mean, I'm just joking around here. I mean, it's really to me, it's. I feel happy if I'm making contact with the results of Turing Award winners because their results have been QA'd probably a lot more than mine have.
Yeah. To me, it makes me uncomfortable to know that I'm making contact with them because it creates all this obligation to learn.
Well, I've spent the last 30 years learning, so I don't mind. Anyway, or learning this domain, so I don't mind at all. But anyway, so that kind of gives you a rough overview of the relationship and kind of history of the modal logics and how they connect to the spatial behavioral logics. And then just since we have even a few minutes left, that's kind of one area of development. And then the other area of development, hang on a second, let me go grab it. Here it is. So I just wanted to point out a couple of different things. First of all, can everyone see this? Can you see this, Vlad? I don't know if this.
Yeah, I see it.
Okay, sweet. So the first observation is just that if you look at the core model that sits inside the Erlang contracting language, what you'll discover is that there's already sufficient structure to give a JSON-like representation. So on the left-hand side, I give kind of a short and sweet summary of JSON syntax. And on the right-hand side, I recap the Erlang syntax. And then in the little equation down below is how you would encode a JSON object into the Erlang syntax. And what it shows is that JSON embeds faithfully into the row core. So you could use row syntax as a storage and a wire transmission format. If you're comfortable with JSON as such a format, and some people are and some people aren't, but if you are, then you would have exactly the same level of complexity embed using the row core syntax. But that also helps you understand, like if you understand that, then you also begin to understand how storage works and the storage semantics itself in the Erlang contracting language. So once you have that intuition, then the next piece of the puzzle comes from, so if you look here in terms of the syntax, we've only utilized the output side of this. So every key value pair is just storing the encoding of the value at the encoding of the key. That's what output effectively means. It means storage, right? I'm putting this value in this channel to be picked up by some client later. Right, and then each of these key values are unordered, and that's equivalent to the par composition as we find here, right? The parallel composition of different threads, right? So this par corresponds to the fact that all of these key value pairs are unordered. So so we've basically only used two pieces plus the value bit of the syntax, but we haven't utilized the input piece. Right. So the input piece is important because what it says is it gives us a syntactic representation of the transaction boundary. So when you execute the input form, what you're saying is this process, this program, this smart contract P is guaranteed to execute in an environment in which we have observed values bound by these patterns from these channels. So this constitutes a transactional boundary for P. Once we understand,
so, can I kind of understand this as like the ABI that we have in Ethereum? It's like a standard in order for so that like different contracts can understand like what they're receiving?
I don't know ABI well enough to say yay or nay. Well, I mean, what I can say is it's just like for comprehensions. It's just like the transactional interpretation of for comprehensions in Haskell or Scala or anything else. It's common. It's a kind of common semantics in the sense that, you know, here we have a bunch of observations that will have to be made before you get to run P, or flipped it round.
Yeah.
P,
So basically, the application binary interface basically says, you know, you have like if you have this kind of hex, and then you need to have like this format of parameters, or else I won't run this function.
Possibly. I mean, the nice thing though is that this corresponds exactly to the contracting language itself, right? So it's a higher level syntax than a binary.
That's exactly what the ABI is. It's basically something that like Solidity respects and Solidity expects.
Okay, cool. Then we're very close in semantics. Now notice that because a P can be one of these for comprehensions recursively, right? And then inside that, you can have a P that's a for comprehension. We can do chains, right? So let's look at what that might look like. So we have a chain of transactions where each of these transactions corresponds to observations, like at this address, I found this value, and at this address, I found this value. So this thing is running in the context in which these observations were made. And then this thing here, i.e. this thing, is running in the context in which these observations were made. So here we have a direct correspondence between the syntax and the actual chained semantics, you know, the on-store semantics that we expect from the blockchain. So the block representation embeds directly into the syntax, and the semantics of that syntax is faithful with respect to what the blockchain is supposed to represent. So that's the next piece of the puzzle, and this is part of this overall step-by-step, correct by construction approach to deriving a monadic or reactive design for the blockchain, so that we can programmers can utilize the for comprehension based access to the chain to get you know, asynchronous stream based access, whether it's from store or from network, right? Where the ports here or the channels here represent an abstraction, so that programmers don't have to be concerned with whether or not this is coming from network or from store, which was precisely the guarantees that were made by Special K. So that gives hopefully that gives a next level of understanding of how this maps out for RChain. And then all of this discussion is summarized. Hang on a second. Summarized in this document here, which walks through the entire semantics from, let me just share this now. So that walks through the entire chain of semantics from, go back to screen sharing. So here we have, here we go, from the contracting syntax through a runtime, which sits just above the virtual machine. And then from that runtime, so from here, which is the contracting syntax, through the runtime to the virtual machine, and then finally mapping that onto storage and network, which is what we have done here. So the entire thing has been mapped essentially from end to end. So you have execution semantics, storage semantics, and streaming semantics all mapped out from end to end with effectively proofs of correctness. I mean, these are not mathematical proofs, but these are what we would, this is sort of the precursor, the English level proofs of the correctness of the semantics. So that's the update on the storage piece.
Cool. Quick question. Probably maybe a dumb one.
No dumb question.
What criticisms do people usually have of JSON as a serialization and storage format?
Oh yeah, well, I mean, the biggest problem is that is the interaction between validation and computational complexity. So if JSON doesn't have types, as soon as you introduce types, then you have this problem because the key value pairs are not ordered. You're going to have to potentially check all orders, and if you don't check them all, when you're validating input, then someone can inject input that you didn't want, right?
So the pairs are not ordered,
right? Because they're not ordered. Now you have this exponential explosion in terms of what you have to check.
Yeah, and in practical terms, Vlad, what that means is like, so I'm talking about it from more of a practical perspective. Everything that Greg said, I'm basically just going to repeat a slightly different way. You can't get two implementations that work together. A lot of times you can get weird bugs where you thought you emitted valid JSON in one context and you did, but then it's used someplace else and it's invalid. And then the other practical thing that happens is that you on a program level are forcing the JSON to come out sorted. So like when I write JSON emitters, I sort it myself, and I just have to make sure in my own code that it's sorted so that, when you're searching for something or you're trying to do something, you don't run into these pretty significant.
Yeah, I mean that's a huge pain in the ass. I mean, imagine you have to like pick something out of a large JSON and you don't know where it is.
Yeah, it's worse than that, right? So it's not just that you get either you have computational complexity out the wazoo when you're trying to validate, but it's also because someone could just go hide some code fragment inside a key value pair that you're not checking for. So you read in the whole JSON, it looks great to you, but unbeknownst to you, there's a key value pair that's in the object that you didn't look for, that you read into memory. That has stuff you didn't want in memory.
And is that something you also check with your emitter and receiver?
Well, that's what you'd like to check. Oh, you're asking.
Yeah. So in practice, I just take that risk, which is what a lot of people do in practice. But yeah, no, it's a horrible problem.
Right. So JSON was a major step backwards for the industry, but what the hell?
It's super standard.
Exactly. Right. It became standard, but it was a major step backwards.
and the win, and it's sort of unfortunate because the win that it gets you is this sort of naive sense of readability.
Yeah.
Right. That's why it's so popular, because you can look at it and feel like you know what you've read.
Yeah. That's totally why I like it.
Yeah. Well, that's why I'm calling this data representation arson.
Lols.
Okay, guys, it's 8:00. Thanks again for another exciting episode of the Casper Stand Up.
Always a pleasure, guys.
Yep.
Have a nice one.
Yeah.
Yeah. Take care, guys. Happy holidays.
Bye-bye.